So we've been looking at run times, computational complexity, how long it takes to run things depending on how you write the algorithm, and at algorithms in general. So, and this is just generally with the idea of introducing you to computational thinking, which can be really helpful when you start getting to more programming and bigger programs, thinking how to plan and thinking this way in terms of algorithms and their complexity, how fast they run, to help you write your programs efficiently and get the best results most quickly. We've been looking at it more general, so let's take a moment here and actually apply it specifically to Python. What's going on with Python? And let's look at some of these, now that we're familiar with some of these complexity issues, let's look at what Python does. So here's an example of just sorting algorithms. And we can use this special, let me change it to a spotlight here. Here we go, that's a bit easier to see. We can change this to, or we can start with this double percentage time, which is a special command to Jupyter to give a report on how long it takes to run a function, to run a program. So this is giving a range. It's taking 9,999 numbers and sorting them. So get a random and then random list of those number of numbers, and then bubble sorting. And with almost 10,000 numbers, it takes bubble sort 16.8 seconds to sort. That's one of the most easy sorting algorithms to program. It's one of the least efficient ones. So you can compare that to the sorted algorithm, which we've learned, which is the default for Python. And I don't know what algorithm they're using behind that, but it's much faster. It can sort a list of 1 million. So we starting here, we can see just the difference. Just starting with almost 10,000, and the difference is, I mean, it's a difference of seconds, 16 seconds and 14 milliseconds, which may not seem a huge difference, but the order of difference is huge. And we can see that it can list, here we have almost 1 million numbers. It can sort a list of 1 million numbers 8 times faster than bubble sort sorts a list of just 10,000. So that shows you, as you increase the numbers, you can see how the computational complexity really is important. The more you grow and use bubble sort, the slower it's going to get compared to the sorted algorithm in Python, which is probably an log n algorithm, one of the best run times you can have. It's not as good as constant time, but it's next best. And we can actually check and see this by looking at the documentation of Python. So there's a link down here. You can go and you can look around at some of the operations that you're able to do in Python now and see what their runtimes are, what their computational complexity is. So we can see a few things here, and this is for list in Python. So you can see, and this really helps to think about, if I'm doing a certain operation and I have so many items that I need to do this operation on in my list or whatever set or dictionary, which of those list, set, or dictionary do I want to use if I'm just considering complexity, the runtime. So you can see, for example, that append is constant time. 1 means it's constant time. It doesn't matter, and that's the average case and the worst case scenario. It's not going to change. 1 there is, big O1 means that it's always going to take the same amount of time no matter how many things you append, which, obviously you're going to append 1 thing. Then we have, well, the get item is, that's actually indexing. It's indicating how long does it take to index into a list. Say you want to get my list, and let's say you have a bunch of items in your list and you want index 4,343. Even if you have 10 million items in your list, it's going to take constant time to index if you know the index. So if you know where the item is in your list, it will not take you any more time to index into that certain item if you have 3 items in the list or if you have 10 million items in the list. So that's constant time. And there's a few others that you can look at, but look down here, we have sort, and this is something we looked at in just a second ago, and this is using the sorted function or the dot sort for list, and we can see indeed it has an log n runtime. So that's a logarithmic growth. It's one of the slowest growths. It's not as good as constant time. It is going to increase as you increase the number of things in your list, but much slower than, say, linear time or n squared time. Here's an interesting one. So here, this is actually a really good one, and we can compare across different data structures. And this kind of indicates other reasons why you might want to use lists or sets or dictionaries, and knowing which data structure to use when is a great skill to have. It comes with practice, it comes with knowledge, and you get more into that in the next class if you take a data structures and algorithms class. So here, for list in Python, the operation of finding an item when you don't know what it is, so if X is in the list, for example, it's going to take in time. So in other words, depending on where that thing is in the list, as the list grows, it's going to take that much more time in the worst case or in the average case to find it. So if you have one item, it's going to take, it's one operation. It's going to be there. It's going to find it. But if you take 3, then, average or worst case, you might have to look at all 3 items. And as you increase to 100,000, tens of thousands, you have to look at every single item. And as your list grows, your complexity, your worst case scenario, your big O is going to grow with it. So that's an in growth. That's for lists. Here's sets. So here's a similar chart for sets. And if we go up here, we see the same operation, X in S. And notice that in set, here we have the average case and the worst case. The average case is not big O in. The average case is big O1, which is constant time. So on average, finding something in a set, if you don't have the index to it, you don't know if it's there, is much better than list. If your list is really big, or if your set of items is very big, because it's only going to take constant time on average. It's going to take the same amount of time to find the thing, whether you have 1 item, 6 items, 6,000 items. That's the average case for sets. So if you have, a lot of things and they're all unique, and you want to, you're going to be doing a lot of searching for something, then a set would probably be better than a list. This is much better for checking to see if the item's in the collection, right? So a dictionary, now a set of course has unique items. Another option, if you have association between 2 things, or you have non-unique things that you can't associate with something, maybe a arbitrary number, then you would rather use a dictionary if you need to find it. So this is the set item here, and of course in the dictionary, this is actually using the key. I don't have the X and M, but it's a similar operation here, and it actually it's very similar to a set. It's not necessarily showing it here, but it's very similar to a set in the fact that the average case, if you're looking for something, is constant time in a dictionary. And we learned about hashing in another video, so it explains a little bit why it's constant time. It's always going to take the same amount of time, no matter how big your set or dictionary is. So that's some application of this computational complexity to Python specifically. And you can go to the website and look around and play around and start to learn about the advantages and disadvantages of the different data structures in terms of computational complexity, which can be really important as you start to work with bigger and bigger text or sets of numbers or whatever it is you're going to work with.